Well, there is another concept in economics which can be treated in terms of partial derivatives. It's the concept of competitive and complementary products. So we're dealing with a situation where there are two products, A and B. The demand for those is affected the price of both of them rather than just one. Demand for A is affected by the price of both A and B, and same for the demand for B. Our textbook changes the direction of the function. In this case, they write Q, the quantities demanded as functions of the unit prices. The analysis works the same way if you reverse that function. But I will just stay with the textbook's approach. So I have the demand for product A per time period given as a function of the unit price of both A and B. So QA is some function of PA and PB. Similarly, QB is a function of PA and PB as well. So we can differentiate each of these functions with respect to either of the two prices, giving us four combinations. Derivative of QA with respect to PA, and derivative of QA with respect to PB, and derivative of QB with respect to PA, derivative of QB with respect to PB. Of course, this derivative of QA with respect to PA must be negative, because if the price of A increases and nothing else changes, the demand for A should fall. Same way, this partial derivative, dQB by dPB, should be negative. But what about the other two? Is it possible that they are both positive? If they are both positive, so first, if dQA over dPB is positive, it means when the price of B increases, nothing else changes, the demand for A increases. And the same way, if the price of A increases and nothing else changes, demand for B increases. So here we have two products. The price of one goes up, people buy more of the other. Of course, it's a very simple situation where this happens, where we have two products which are competing with each other. So products from two competing manufacturers. So if one manufacturer increases the price, the other doesn't, then some consumers will switch to the other manufacturer. Another situation where this happens is where the products are what are called substitutes. So you can use one in place of the other, even though they are not exactly the same. For example, like butter and margarine. If the two cross partials are positive, they are competitive products. What if they are both negative? So if the price of one increases, the demand for the other falls. This looks like it's a strange situation, but some thought will explain why this can happen. An example of this are gasoline, tires. If price of gas goes up, then people would drive a little bit less, which means tires don't wear out as quickly, so demand for tires tends to fall. The reason why this happens is that you cannot really use tires unless you are driving your car, and that requires us to use gas. So we use the two products together. So such products are called complementary. So if price of one going up causes the demand for the other to go down, you generally have a situation where the two products are used together, not alone by themselves for the most part. You might wonder if it's possible for one cross partial to be positive, other negative. Mathematically, yes, but actual situation, it's very hard to come up with examples of that, and we won't worry about this. Again, the problems in the textbooks are simple calculational problems. They give joint demand functions and ask you to decide if the products are complementary or competitive. So you just calculate the cross partials and see if they're positive or negative. We will do a couple of simple examples. The first one is QA equals 20 minus PA minus 2PB, and QB equals 50 minus 2PA minus 3PB. We will just do the cross partials. So the partial of QA with respect to PB, I just go term by term. The first term is a constant, its derivative is 0. The second term I have only PA. I treat that as a constant when I'm differentiating with respect to PB. So there also I get 0. In the third term I have 2PB, its derivative will be negative 2 times 1 or just negative 2. The other cross partial is the partial of QB with respect to PA. where I have 50 minus 2PA minus 3PB in the function. So when I differentiate, I get 0 from 50 minus 2 from PA and 0 from PB. Because I'm differentiating with respect to PA, I treat PB as a constant. The first term I have absolute constant 50. Second term I have minus 2PA, the derivative is negative 2. The third term I have only PB, I treat that as a constant, its derivative is 0, so I just get minus 2. Since both cross partials are negative, these are complementary products. The next example is 200 minus 3PA plus PB and QB equals 50 minus 5PB plus 3A. So derivative of QA with respect to PB will be 0 minus 0 plus 1. I will leave it to you to figure out what I'm doing. Partial of QB with respect to PA is 0 minus 0 plus 3, or just 3. Both cross partials are positive, so these are competitive products.